I realized I hadn't shot video of this thing since I've made several improvements to it. There's now a little transparency sheet in here with double-sided tape to kind of act as a deflector. If someone were to drop something, it would hopefully not land in the cap bank. There's a normally closed capacitor drain relay and main power relay. So there's an emergency stop switch on top here, a mushroom that you can hit to cut power to the whole system. And that will disengage completely by triggering a cut to this coil that will return to normally closed position, shunting the load from the capacitor bank and whatever capacitors I have hooked up out here through these two 500 watt resistors, mil-spec guys. And this bank drains down so quick, it's not even enough heat dissipated for them to even get warm. So once I get my bigger capacitors hooked in here, this will be a good way to, like, you cram e-stop, and even through there, it's all going to go through this into the resistors and drain out. And make safe, whatever got connected to this DC side. That also means whenever it's off, this is just basically a giant resistor connection. But at rest, this is safe, and the resistors are shorted through, or shorted to the caps. And then I've got my coil power control that comes from the front panel e-stop input. So from the e-stop circuit, this is power feeding into the front panel. And then the rest of the front panel connectors here. So there's two flying legs, because I don't want to drop a whole other bulkhead in here just for two legs, and the rest. And I've just added a RF filter to the entire thing. So all the incoming power goes through this RF filter before it feeds into the entire system. So when I run a Tesla coil off this or something else, just to the AC side, obviously I'm not using the DC side for that, then it'll filter the power going out. So now I'm going to finish reassembling this, and hopefully it looks real pretty. I can show you a comparison. All right, here it is. We'll put the final finishing touch on and drop in this panel bulkhead cover, and voila. So now you've got all front panel connectors here. They terminate here, and there's even that plug I told you about earlier that receives power from the e-stop circuit to the control circuit to actuate the main coil and the relay. So here's how the whole thing looks. I'm going to close it up, and you've got that nice little, kind of get out of the way there. I don't have a thing to retain it, but that's good enough. And that's it. So now it'll fully function just like it did, but the difference is now we've got EMI suppression as well as a tank drain circuit. So as soon as this is turned off, or whenever you slam the shroom, you get tank drain immediately. I'll show an example of that on video. It's not a very loud relay, but when it's engaged you can hear it. So e-stop works. This light is directly, well, it looks pretty dim on camera. It's very bright in person, real live here, but the e-stop switch directly powers the LED. So even if all this circuitry is disconnected, that light will come on no matter what, because it's directly between a normally open contact on this and neutral. So as long as you've got power and you e-stop it, you're going to see something here. So normally, if I'm doing work on something, I can e-stop this, and if I see the red light, I know that the entire system is disengaged. That powers it up. Nothing has been done yet, because in series with the e-stop circuit, I have to close this. I just heard the main relay click, so I've got power. So the AC side is working. You watch, I'm going to turn on the DC tank, and we'll charge this thing up. Watch the tank voltage. Put some current in this thing here. Get up to 150 volt, and I'm going to slam e-stop. Not instantaneous drain out, but that's not what I was looking for, right? So those resistors drain that down really quick. I think if you saw in the older video, it would hang there and just set. And I mean, it would be hours before it would drain 10 volts at that amount of capacitance. So this is a necessary step in safety, to have the kilojoule bank I plan on building at these voltages. So 1 kilojoule at about 170 volt DC for some other stuff. But that is unnecessary right now for the Tesla coil things. That was really why I added the EMI filter, because most of the time I won't be using the DC side, I'll be using the AC side, and you'll just see this. And that'll be it, I mean, for 90% of stuff. So either way, same thing happens. Hit the e-stop, entire circuit cuts, everything's disengaged. So pretty nice safety feature to have a little e-stop on there. I think that's complete. I'm going to quit opening this thing. I'm done touching it. I'm not going to add anything else to it. I will call that finito. I ordered a neon sign transformer on eBay, and I think this gets qualification for the best packaging I have ever seen. It was a box that was tightly wrapped cardboard box, and it had been stapled to this. So I was like, oh man, this is a really dense box. Like, this must be padded something crazy. He built a wooden box. The guy I bought this from built a wooden box, and it had 6 screws, and the whole thing's just like, it's all screwed together. So I pull all 6 screws out, and then inside, after cutting that duct tape, there's the transformer And he's used insulation block. This is like the best packed transformer I've ever ordered. You don't find many people doing this. This is obviously an older guy. The pictures had a really old hand. So this guy's probably in the 70s, but I wish when I bought stuff on eBay it was packed like this more often. This dude packed this like it was getting ready for international shipping in the 1920s. I am stellar packing, man. If you're shipping transformers on eBay, man, that's the way to do it right there. Alright, so here's our test setup. We've got the neon sign transformer connected to power supply. So power is live right now. Go ahead and turn on the AC side. Start at 30 volts just to give us a reading here. High voltage, and the way that these probes work is, I double the ground. So this is center tapped secondaries to ground on chassis. So one side, yep, that's almost a kilovolt. That's 700 volts right there with this probe. That's a dividing probe. So we're going to amp this up to 120, right where it should be. And then check this. There we go. 3.5. 3.5. I feel a good hum coming through that transformer there. This side. 3.5. Good. Okay, so that means 7 kV right there. Let's bring this up just a bit. Drive it up just a little further. This is supposed to be about 9 kilovolts, but there you go. 3.8. Let's go a little higher. Sometimes you got to drive a little hotter to get the actual rated 9 kV. So I need 4 kV per side. You can feel some good humming coming from the table. There we go. 3.9 kV. 3.9 kV. I would never recommend doing this without, turn it back down to 120, without a high voltage probe. So the way that some people will test them, and you can test them this way, 3.5 kV, would be to, okay, now that we're done, I told you the red light was my friend. I like the red light being on. I still turn the variac all the way down and turn off the power. So I'd not only have to uninterrupt that, I'd have to disengage the mushroom, I'd have to flip that switch, and I'd have to bring the power back up to re-energize this. And I can check now. She's dead. So what you could do for this, and what some folks would tell you to do, is you take each side and with a non-conductive probe try to short and draw an arc off the chassis. I was just going to tell you if that side's hot. You can have varying voltages if the windings on it are shorted or have some kind of issue. They can still work if shorted to some extent. They're just going to have the wrong voltage and it won't put out the right current. In fact, I have some examples. Deal was too good to be true on eBay. This one, unfortunately, was only for 30 or 40 bucks, and it's got one good side and one bad. And I'm just, what's this? This was 7.5 kV, so that's both together. So divide by 2, it's basically useless. I might as well just use and plus what was this, 30 MA? So I might as well just use a 10 kV oil burner ignition transformer. This one is completely fried. I was really hoping this one would work. This is a 15 kV 60 MA, and it was relatively cheap. They're just not worth rewinding. The primary and the secondaries are fried on this. I think someone must have used it for Tesla coil stuff or something. It is completely shot. Secondaries are completely open. The primary is even completely open. It's either struck by lightning or something, but that is the worst I've ever seen. This one was also bad. So, you win some, you lose some on the gamble of old NSTs. You can buy newer ones and disconnect the GFCI, but, I just figured I'd try some of these older ones I found that were really cheap on eBay. And the one I just got, the gentleman, I said, the older hand the guy had, he was actually drawing arcs off it. I'm like, all right, well, that's obviously good. He showed pictures of both sides drawing arcs. I would not buy one of these if it's not been tested. I didn't realize eBay has gotten so bad now. It used to be I could buy these and they'd be halfway decent off eBay, but there's your warning. People don't have the tools to test them. They don't know how, unless you find somebody who used to own a neon sign shop. When I saw the guy's bare hand drawing an arc off this, which, by the way, is stupid, but if you've been working with these things for years, guys like that just don't care. I would never do that, but yeah, there you go. You see that kind of craziness, like, oh, that dude's obviously been working with these things so long he doesn't even care. But yeah, mileage may vary. Be careful on eBay.